Hello everyone. So I am Mathieu Baumann, software engineer, and she's Manon Marchand, software engineer too. We both are part of the CDS, the data center of the Astronomical Data Center of Strasbourg. So it's based on in Strasbourg at the east of very east of France. At CDS, we are a data center, so it means we store astronomical data set, such as tabular data of astronomical objects like galaxies, clusters of galaxy stars. We also store images of the sky, and we also develop tools to visualize this data. And for example, what we are going to show you is a tool to embed the sky into a notebook. It's called ipyaladin. So just before talking about ipyaladin, I would like at CDS we have that vision to develop tools to visualize the sky since the beginning, so mid-90s, where we had a first publication mentioning the Aladdin project. So Aladdin is a project to see, to have an interactive view of the sky, to pan the sky, to zoom towards the sky and see more refined images of the sky. And so there is, since that time, first very first prototype done in C, and then a more full-featured desktop version, Java desktop version. It's called Aladdin. You can see, you can download it on our website. You can see different parts when you open the application. You have a data discovery tree on the left, which allows you to search for tabular data to display on the sky, and also to search for surveys coming from different telescopes, such as the James Webb Space Telescope or the Hubble Telescope, in different wavelengths also. And on top of that image survey, you can plot catalogs, so tabular data. Like you can see here some arrows. These are vectors that refer to proper motions of the stars. It means speed of the stars, its direction, and the magnitude to the vector shows the speed of the stars. There has been also, since the advent of web, there has been a JavaScript web application called Aladdin Lite, which has been developed since 2013. It has been fully JavaScript first, but a few years ago, we completely rewrite its rendering engine in Rust with direct access to the GPU thanks to WebGL2. It's compiled to WebAssembly and then wrapped around the JavaScript API. This is a totally open source project. You can find, so we have a GitHub repository. If I go on it. So this is our GitHub repository of Aladdin Lite. You can see there is API documentation with to embed it if you want to embed it into your own web project. Sorry, you have a series of editable examples. So here you have the JavaScript to create that Aladdin view. So you can pan here, zoom. You can change on live, for example, the field of view. Let's say I want 10 degrees to start with 10 degrees of field of view. It's written here. So it automatically changes the corresponding view of the Aladdin Lite div element. And so there are release pages, there are, so it's open to contribution. Just to show you another example, you can do you can add multiple surveys on top of each other and change the opacity of the top one respectively to the one on the below. You can change the things like the color map by right-clicking. By right-clicking, you can change the cuts to see more refined galaxies. So let's go back to the slides. So how does it work? So you can see here there is a zoom toward a specific cluster of galaxies, and you can see this tile that are loading. So they are fetched. The more you zoom, the more you see the tile images appearing. So here we have some. The tile are not displaying correctly, but they should appear.
Yeah, so it depends on the internet connection, and it's a bit slow.
But yeah, and here you can see an image of the James Webb Space Telescope. So the idea is you will only download tile images that are inside the viewport. So, and this relies on a specific tessellation of the sky, which is called the ILPIX tessellation. You see it's a hierarchical tessellation. So we begin with subdividing the whole sky into 12 images, 12 cells, which are equal area. And then at different orders, you will subdivide each ILPIX cell into 4, which gives you 12 by 4, so 48 tile images at order 1, and you each time subdivide it into 4. And that's the way we at CDS create this ILPIX sky maps of different surveys. And so we did produce more than 1,200 images, ILPIX sky maps, and it represents 750 terabytes of images. So Aladdin Light has been used as a rendering engine in several web portals, including ESA Sky or the ESO Science Archive. And it's also being used recently by people working on the James Webb Space Telescope for their outreach visualization tool. So people from the STS CI. And it represents approximately 30,000 startups a day. So it's deployed as a standalone JavaScript file and also as an NPM package. And that NPM package is used for ipyaladin widget. So you can see here a GIF showing there is a Python API which allows you to set the FOV, to set the survey, to query for a catalog around a specific galaxy and a specific radius, to add the table, change the projection, and do many more things that Manon will show now.
Yeah, so now we jump in demo, and I will show you the Python API for Aladdin that Mathieu just presented. And he forgot to say that he's the main developer of Aladdin Light, so the Rust and JavaScript part is made by Mathieu, and I'm more in charge of the Python API around that, so the wrapper. So I will jump out of the presentation mode, and we're going into live demo. So here you have the Jupyter widget on the side, and it's working on the same kernel, but the presentation, which is also a Jupyter notebook. So what I did right now is that I just imported our widget already, and I put it on the side. Now what we can do, or what Mathieu said, is that we can set a target, and that is not trivial because I'm here sending a string, and I need coordinates to know where that is. So that is one of the first things that our database does, is that you can give a string, it looks into the literature data, and it gives you the coordinates. So let's do that. So I sent a request to our database, and I got coordinates back, and if you saw, the widget moved. But I still don't see the Perseus cluster, which is the thing that I requested here. And what is the Perseus cluster? It's a cluster of galaxies. So far, I don't see them, so I can zoom into the GUI and see what appears. And what you see, if you have an exerted eye, is that some of those spots are quite blurry, and that is characteristic of a galaxy. So some points are stars, some are galaxies, and what we will do later is try to characterize the galaxies in this cluster by using the widget. And so the first thing I can do is store the result that I got for the target into a variable, so that's what I'm doing here. So I got it. If you notice, I sent a string to the JavaScript API, and I got an AstroPy coordinate object as a result, so something that is more structured, and we can do operations on that. Now, let's also say that I want to find a relevant field of view, so how large the cluster is, around, like grossly, just to start exploring, having some numbers. So if I unzoom a little, I see that I don't have galaxies anymore, so I will like go to approximately this size. Sorry, I right-clicked. And now I'm storing that field of view in a variable too. So I got something like 20 minutes of arc, 26 minutes of arc, and we will keep that later. So once again, I queried the JavaScript API. It set me a float, and that float I can put into AstroPy, which is a Python module for astronomy. And this gives me something that I can use, which is higher level, because it converts that float into something that is angles that we use in astronomy to describe distance in the sky, because it's a sphere. So now that I've got that, what I can do is so this is what I just said. We sent a string, we sent a float, and we got complex Python objects that I can use later. And now that I've done that, what I can do is explore a bit the GUI and try to see if those galaxies are already known in the Simbat database that we host in Strasbourg at the data center. And this I can do one way, which is not really reproducible for now, but I can get that target here that I got on the side and click on something. And this, again, sends a request to Strasbourg Data Center, and I get an answer back. This is the name of this galaxy. It's called NGC 1278, and it's a type galaxy in a group. That's perfect because we are looking at a cluster of galaxies, so this means that I can get information on individual objects. But that's not really something that I can mass do on my widget. So let's look at the Python API to access this exact database that I got by clicking. So if we resume, I can send coordinates and get information on objects. So it works both ways. I can send a string, get the coordinates, send coordinates, get information. And that's what we're going to do with AstroQuery. So now what I'm doing is that I'm connecting to the Python API of this database, and I'm saying that I want to see which galaxies are known in the literature of astronomy around the target. So this is the variable that I stored by using the radius, that is the field of view that I got from the widget. And I'm also saying that I only want galaxies, which is this string that you have there, that you have to learn how it works. So I sent my request, I got my answer. This is quite fast. It says that in the database we have 418 galaxies in this radius. And what I can do after is that now that I have this table, I can add it to the view. So this is exactly what I did, but the cell didn't appear. Yeah, sorry, forgot to make the cell appear. So this is what I just executed. So I'm using Aladdin. I say that I want to add a table. I give the table, and then it's cosmetic things. So the name of the table and its color. So you see that around here, I have quite a few galaxies that are known in the literature that are in our database, and I can get information on them, just like before. So I get the coordinates, I can click on them, I can select some of them, like Mathieu showed you in the GIF before. But what I want to do is that I see that some of them, like they look blurry, they might be galaxies, but they are not known in that database yet. So what we can do is look at other sources of data. And so what I'm going to do next is that we are going to go into trying to find more information about this cluster, but by looking at other sources of data. And this is where the widget shines. It's because you have something that is quite visual, so you can overlay different sources of data and different kinds. Like I forgot to say, but we got an image that came from the data center. The base image is DSS survey. And we also put a catalog on top of that. And we all are going to add on that. And what I propose for you is that we're going to go through the wavelength spectrum, but also go through features along that. So we will start into radio, and we were going to go up to X-ray by looking at some features. So the first thing is I'm going to go into radio and Euclid data, which is visible and close infrared. And the first thing I'm going to do is change the survey at the bottom. So we had the DSS, which was optical, so close to Gaia in wavelengths, comparable to that. And I will change that to the Euclid telescope. That is quite new. And we see that we have a different image that appeared. So I sent the request, and I got the image back in a second, which is actually amazing because this image, if I unzoom, is 6 gigabytes in its most defined resolution. But just as Mathieu said to you, we only load what is needed. And so if the size of the pixel would be smaller than the pixel that I can show on the screen, then we don't show it. So we got something that is degraded. And when I zoom in, it's actually sending requests live and getting the information as I'm zooming in, until it doesn't anymore because we go to the resolution of the satellites. So we see that some of the galaxies are known already, even in this very recent survey, and some, this is blurry, and I don't think I have a green point here. No, I do. This one is also known. But if we go to the very zoomed one, then some of them won't be known. Like, for example, this is a galaxy, this spot here. And so what I can do is choose a region of interest and maybe overlay the survey that we had before. So I'm adding another one. And this is the default one, the optical survey. And I can change and see if this is a galaxy that could have been observed in a less resolution. And this is not the case. Like, for example, some of them, if I zoom in a lot, they have to be new. So there is new science to discover there. So this is how we do. And what I'm going to do now is that I loaded the image on the widget, but I can't do science on it because I don't have it on my disk. So I'm going to download that. And so I'm saying that I want the image of what I'm seeing right now in this exact position and download that. So this takes more time because we're getting a lot of pixels. Let it download, so we got it. And now, for example, we can plot that into a matplotlib thingy and see that this is exactly what we're looking. If I remove the stack and if I remove the selection, you see that those pixels are exactly the ones that I selected with the interactive GUI. And they are scientific pixels because we didn't take the pixels of the widget, we queried the database and we got the scientific pixels back. So that was scientific pixels, but we can also go in our journey of wavelengths and explore another telescope, and we will look at the ASCAP telescope, which is radio. To do that, I can do it with the GUI. So I do add a survey again, but this time I use the browse button, and I type the name of the survey that I want to find, and let me do it like that. And it looks very different in that wavelengths. You see that we have a source here that is in the middle of the cluster. So this is a galaxy cluster that emits in radio. We get a strong emission in radio, but we can't really see individual galaxies. So that is another information. We switched completely the appearance of the sky in that region by looking in different wavelengths. And that's kind of the things that we can do. We can still change the opacity and see that indeed this is the middle of the cluster. So now I can also save that thing, say, okay, I found that the middle of the cluster is close to this radio source. So I would change the opacity. And for example, this shows that very well because I have the two of them. So this time I'm saving the screen, the pixels that are on the screen, and then not the scientific pixels. So let's do that. So I now use save view as image and not as fits, which was the scientific format for astronomical images. And I'm reading that again, and we see that this is indeed what I have in the view. Sorry, I'm gonna, no, where is my, sorry for that. So far we put in different kinds of images, but they all came from our database. And now what happens if I want to work from data from my disk that I got directly from a survey that is not yet publicly available, for example? Sorry, that is the next part for Chandra. Now I'm gonna show how we work with catalog data. So this time I'm changing the telescope that I'm using. This time it's in optical, and I'm gonna see if there are more galaxies that are known in that catalog that are not yet in a paper. So not yet in those green ones here. And I'm using again AstroQuery, but to a different database that we also host in Strasbourg, and that is the galactic candidate, so GalChem, in Gaia, the telescope. So when I do that, I'm sending the query, and it says that for the field of view and the target that we got, we get 157 candidates. And if we look at the table in more details, we see that some of them have the flag galaxies. So the consortium that published this data is sure that it's a galaxy, and some of them, they are not very sure. So let's put two different colors for those two different categories on the widget, and that's what I'm gonna do here. If you look, I use @table just like before, but I'm putting two different colors depending on we're sure this is a galaxy or we're not really sure in the precedent survey. I'm hiding the radio data because it was quite hard to see the galaxies on that. And we see that we have some pink points when we are not sure it was a galaxy with that telescope, and a blue one when it was sure. If I zoom, I see that in Euclid, it becomes more clear which ones are galaxies and which ones are not. So we could add science on that and say, now I'm sure this is a galaxy, and contribute and flag that. To do that, for example, I would select the point that I'm interested in and that I want to keep in the Python side. So those are in the JavaScript part, and I can select on the interface something in a circle and get the points that I find very interesting. And when I execute that cell, it will request from the JavaScript the table that I just got. So it's the sub-selection, and the first one is 4 galaxies that we are sure are galaxies from the catalog Gaia, and the second one would be the ones where we're not sure. And now I can analyze the ones that I identified on the widget more specifically. So if we see of what's happening, we are really exchanging data from between the two sides, the JavaScript part and the Python part, and I can do the analysis in the analysis where I feel more confident. So now I'm going to the other end of the spectrum and the end of the presentation. Now we're using data on disk and not data from the data center. And this is an image in the fits format which has information about where to put that on the sky. And this would look like that. So I'm calling fits.open, which is from AstroPy. And then I'm using @fits from Aladdin. And this put the image in the right projection. So it took the original projection from the image and it converted that to the sinusoidal projection that we're using here. And it got me the image in the right place. Let me hide a few things because we have a lot on the stack. So let me, for example, hide the candidates and galaxies, and we can look into more details about what we see here. And we see that in the X-ray regime, so we're in the X-ray now, there is something very interesting around one of the specific galaxies that is known in the literature, which is this one, 3C44, so 84. And we see dark spots around. These are shock waves. So this galaxy might influence the others that are around. So what I can do now is that I will draw on the widget the zone where I see those shock waves, and this can be done with the selection tool. I will remove that so that it's easier. So let me draw around. So that's something, for example, that could be used for image segmentation. If people have applications in machine learning, you can segment the image like that. And then you can retrieve that by saving on file this that I just created here. So let me overwrite. So I saved my polygonal selection, and then I can read that again and get that into Python. So I'm doing this here. I'm loading the file that we just saved. And then I'm creating a mask by saying if the coordinates of the green points are in the selection, then I want to keep them. So when I apply this mask and I add the table again, I see that only the ones that are inside are kept. And now I can select on very complex shapes things on the sky and keep that. And this is the end of the demo. I hope that you loved it. I have a few words. you can. Thank you so much. I have a few words on how this is made because we are built on the shoulders of giants, and we didn't make the widget from scratch, of course. There is the NPM module that Mathieu is the main maintainer of, and so we connect to the public JavaScript API of that. We make the widget with anywidget, which is awesome. It's a wrapper on the top of ipywidget. So maybe most of you know of ipywidget. We use anywidget that offers us a more general way of maintaining into different notebook platforms because of our users. They want to use Marimo, they want to use Panel, they want to use Jupyter Lab, and that was a nightmare. At one point, we spent all our time maintaining that and not implementing new features. So since we changed, we have new features. And that's awesome. So I love anywidget. Please go and check their repo. And then I want to also sum up that the ipywidget framework, they do the conversion of very simple data types between JS and Python for us, like floats, strings, objects that are converted into dictionaries. But then if we have more complex data types that are specific to astronomy, we need a parser in those two, in the two languages, and EO in the two languages. And that's quite okay also to implement, but it's something to have in mind if you want to make your own widgets. And now we are at the real conclusion. We have a way to analyze data interactively, but also you can keep what you did on the Python side if you want. It can be super useful for image segmentation and building data sets because we can download snippets of that, and we know that it's used for that a lot. And then there is the exchange of data between the two. There are more features on our repo, so please have a look and come and chat with Mathieu and I. We love talking about Aladdin and astrophysics, so yeah. All questions welcome.
Thank you. So we are 5 minutes late because we started 5 minutes late. It's not
okay.
your fault. Yeah, it's because we started late after the break. So maybe while we change speaker, if you have some questions.
Thank you. Thank you for the great talk. I wanted to know, so if I understood clearly, so we can have this visualization tool of the different surveys, and then on a notebook we can also have, let's say, some selection of galaxy we want to identify in the visualization, and so this can render kind of automatically. Let's say like I click on the galaxy and then I have a model that tells me all the galaxies that are similar for given physical properties, and then I can visualize these galaxies back in the...
Yes, so you would need to write that the target is the galaxy that you have in your model and move the target of the widget. You write that just like we did in the first cell. Same for the field of view. If you know the extension, the apparent angle of the galaxy, you will put that in the field of view, etc. You can also download the snippet if you want, getting either the scientific pixels or the non-scientific ones as you prefer. You can annotate. The only thing that we didn't automate yet are the selections. Like the thing that is done is the selection is always in a Python variable, but we can't move the mouse yet with the Python API, but that's something that we're going to do. And we're like, if you need anything, open an issue.
Okay, thank you.
Or contribute, we would love that too.
Okay, it seems awesome. I'm eager to use it soon. Thank you.
Okay, so if there are no more questions, we can thank our speakers again.